Bismillah. Assalamu alaikum. Second lecture for in our last lecture we talked about basic block diagram, the basement is block diagram system. In today's lecture we will be talking about the functions of individual blocks used in. So let us start our discussion. Simple process. Sampling is actually the process of converting analog signal into a discrete time signal. So what we do, so say for example this red line represents an analog signal. So we calculate the samples of this analog signal at specific time instances, which is named as sampling time or sampling interval. So typically we use a uniform sampling interval for sampling processes. So this interval between is constant. So so each samples, it corresponds to the specific voltage level at that particular point. So for example, the first sample it shows the voltage at this point, second will show the voltage at this point, the voltage at this point on. Each samples uh, each sample would represent the voltage level at that particular time, which will later on be converted to binary number by using quantization process that will file. So there are few important things or terms which are related to sample. So sampling is the process of converting continuous signal to a discrete time samples at discrete time intervals. So the sampling, if it's not properly done, in that case sampling may cause some distortion. However, there is a certain theorem which is called Nyquist theorem. If that theorem is satisfied, in that case the sampling does not cause distortion and the signal can be recovered from the values of the function at the sampling point. The sampled values, the time interval that we use for sampling purposes is known as sampling. So this maximum sampling interval actually depends on the maximum frequency component in the signal for proper reconstruction of the sampled values, as discussing in the Nyquist sampling theorem. Sampling rate or sampling frequency is the frequency of sampling which is performed during the sampling process, which actually mathematically is defined as the reciprocal of the sampling interval. So sampling frequency is generally measured in terms of samples per second. So how many samples we collect in a second while we are performing the sampling. So at this stage now we discuss the Nyquist sampling theorem or Nyquist criteria. As I mentioned that if we do not perform sampling properly, in that case there is a chance of having distortion. So what do we mean by sampling properly? That means we have to adjust the sampling rate in such a way that we do not lose any information. So what should be the value of this Fs sampling rate? It is defined by the Nyquist sampling theorem. The Nyquist sampling theorem states that if the signal is sampled at the rate at least twice the maximum frequency, so whatever maximum frequency component is there in the signal, if we sample at least twice the sampling rate, then the waveform can be exactly reconstructed from the sampled. without distortion. So for proper reconstruction of signal, it is important that sampling is performed at the rate which is higher than the double of the maximum frequency component in the signal. So this value, this cutoff value of 2 FM is named as Nyquist rate. So sampling rate should be greater than this Nyquist rate, otherwise it will cause distortion in the signal. So how does it cause distortion? If this Nyquist rate is not satisfied, that is if Fs is not is less than 2 FM, in that case we see that there appears some overlapping between different spectral component in the sampled version, and that overlapping is named as aliasing. So that frequency domain overlapping causes distortion in the recovered signal, because the signals do not gets recovered properly because of that overlapped part of the other samples. Theoretically, this Nyquist criteria is sufficient condition to allow signals to be reconstructed completely from the set of uniform samples. However, for practical purposes, keeping this barely minimum value of 2 FM is relatively a harder condition to achieve, because in most cases the signals that we work on, they are not strictly band limited. So for practical purposes we generally use the sampling rate which is somewhat higher than this Nyquist sampling rate. For a typical value, we may take Fs to be equal to 2.2 FM, that is almost 10% extra samples for the reconstruction. This is the most practical consideration that we use for practical purpose. So let us take a simple problem here. Find the Nyquist rate and Nyquist interval for each of the following signals. So we are given two signals here, and we want to find the Nyquist rate, that is the Nyquist frequency, as well as the Nyquist interval for this case. So let's say our signal is given as this value: 5 cos 100 pi t, cos 1000 pi t, and t. We know that in order to calculate the Nyquist rate, we need to find the maximum frequency component. You can see that we can simply use the product to sum formula of trigonometry to convert this expression into some form here. So we will be having a difference of terms and a sum of terms with half of the amplitude, 2.5. So from this term we can see that for the first term omega is 3000 pi, whereas for the second term the omega is 5000 pi. So this one represent the maximum frequency content in the signal. So MT is actually band limited with frequency of 2500 Hertz. As you can see that F is actually 2 pi, omega is 2 pi F. So from there we can easily calculate frequency. Hence the Nyquist rate is actually double of this value, which is 5000 Hertz, and the Nyquist interval is actually reciprocal of this Nyquist rate, which is 1 over 5000 second, which turns out to be 0.2 milliseconds. Similarly, for this function 200 pi t, actually in frequency domain it is represented as this function, rectangular function. So this signal is band limited. You can see from the frequency here 200 pi t. So it has a band limited frequency of 100 Hertz. So because the maximum frequency content in the signal is 100 Hertz, we can say that the Nyquist rate is double of that maximum frequency, which is 200 Hertz, and Nyquist interval is 1 over 200 seconds. Okay, let us turn back to the previous example that we were taking. So once the sampling is performed, the next stage is to quantize the signal. So next process is the quantization process. In quantization process, we transform the sampled values into a predefined number of levels. So say for example we have defined 16 voltage levels here starting from number 0 to number 15. So we have defined it to 16 different voltage levels. So each level, each sampled value will be rounded off to one of the voltage levels. So say for example this can be rounded off to the 6th voltage level, this sample, this can be rounded off to the 4th voltage level, this one can be rounded off to the 3rd level, and so on. You can see that this one can be rounded off this 12th voltage level, and so on. So each sampled value will be rounded off to the nearest voltage level, and this process of rounding off is named as quantization. And we use an encoder to transform this quantized voltage level into the binary digits, calculate the binary equivalent here. So you can see that corresponding to each sampled value after quantization process, we will be getting a specific number of binary digit corresponding to each sample. For example, this one relates to it can be rounded out of 12th voltage level. So from this sample we will be generating a binary sequence of 1100, which corresponds to this voltage level number 12. Similarly, this one can be rounded off to this 5th voltage level approximately. So you can see that the binary digits which is generated from this sampled value after quantization is actually 0101, which corresponds to the 5th voltage level. And you can see that each of the sampled values after quantization process can easily be converted to the binary digits by using that encoding scheme, and each binary digit can easily be represented in form of pulses. So typically this representation in form of pulses is named as pulse code modulation, or PCM. So sometimes this entire process of sampling and quantization is named as M. So quantization is actually the rounding off process, as I just explained, but whenever we round off the sampled values, of course there will be some error in the signal. This error, which is generated in the quantization process, is generally named as quantization noise. As we have previously discussed, that in case of noise, the performance parameter is signal to noise ratio. So because we are talking about the quantization noise, the performance is generally measured in terms of signal to quantization noise ratio, or SQNR. Typically this SQNR depends on the quantization levels. For example, if we have used 16 voltage levels here, so we will be having certain quantization noise levels. If we increase number of levels, for example if we use the 32 levels for this particular case, we will be having a better value of signal to noise ratio. That means the effect of noise will be reduced in that particular case. So how do this signal to quantization noise relates to the voltage level? So mathematically, if we divide the average signal power to the average noise power, so SQNR is given by this expression 3L square by 2. So this is the relationship between signal to quantization noise ratio and the number of voltage levels that are defined in the quantization process. And you can see that each sampled value is transformed into a number of bits. For example, this for 16 levels, this each level generates 4 bits. So we will be getting 4 bits at the output corresponding to each of the sampled value. So typically the relationship between the number of bits which are generated from each quantization level is defined by this expression, that L is equal to 2 raised to power n, where L shows the total number of quantization level, and n represents the number of bits which are used in this expression. In most cases, we prefer to represent signal to quantization noise ratio in decibels by simply taking log and multiplying it by 10, as we used to do previously to transform the signals into the decibel values. So if we calculate the signal to quantization noise ratio in dB, we see that by taking 10 log of this function, we would end up with this result 1.76 plus 20 log L. So this is the mathematical relationship to represent the signal to noise ratio in decibels. As we know that L is related to the number of bits, we can use this relationship, simply substitute L by 2 raised to power n, and the same expression can be represented in terms of number of bits as well, which is 1.76 plus 6.02 n. So this is the mathematical relationship to calculate the signal to quantization noise ratio. Let us take a simple problem to understand how we determine the quantization noise ratio and number of levels in a certain case. Typically, each application requires a specific value of signal to quantization noise ratio, which is mentioned in this problem as 40 dB. So we are given that in a binary PCM system, the output signal to quantization noise ratio, that is SQ&R, is to be held to a minimum of 40 dB. So we need to have at least 40 dB of SNR. The better can be used, but we cannot go below 40 dB. Determine the required number of quantization level, that is S, and we also want to find the corresponding output SQ&R. What will be the resultant value of the signal to quantization ratio. If we use this expression here, you can see SQ&R in dB is defined by this relationship, that is 1.76 plus 6.02 n. So we are given this expression there, and for this particular case, we need to have SQ&R to be greater than 40 dB. You can see that this relationship is already in dB and 40 is also in dB, so we do not need to convert any value in dB or vice versa. From this relationship, you can see that n can easily be calculated, because n will be 40 minus, subtracting this 1.76 there, 40 minus 1.76 divided by 6.02, and if we simplify, we would see that so we need to have number of bits to be greater than 6.35. This value comes out to be 6.35. So that means for this particular case, we need to use number of bits which are greater than 6.35. So we cannot use 6, rather we should take the value n is equal to 7 for number of bits here. So how many quantization levels will be there? So we can easily calculate those quantization level now. That will be L is equal to 2 raised to power n, that is 2 raised to power 7, comes out to be 128. Now we can use this value to calculate the signal to quantization noise ratio again for the for number of levels of 128. We know that the signal to quantization noise ratio is given as this X formula. So if you use this, SQ&R is equal to 1.76 plus 20 log L, which is 1.76 20 log 128, and if we simplify, we would see that the resultant SQ&R comes out to be 43.9 dB, which is actually greater than the minimum acceptable value 40 dB given in the problem. So this was a brief discussion related to sampling and quantization process. So this is the overall illustration of pulse code modulation here. So pulse code modulation is the name given to the class of baseband signals that we obtained from the quantized pulses by encoding to digital world. For example, we have an analog signal. So first we pass it through a low pass filter in order to band limit that signal. then we pass it through a sampler, because sampling have represent the information in form of amplitude. You can see that the diagram of sampling which was illustrated here, each sampled value has a different amplitude, so information is basically contained in this amplitude. So sometimes uh, this sampled output is also called pulse amplitude modulation or PM signal. Then we pass it through quantization process as we previously discussed, and then we use an encoder to transform those quantized levels into binary digits. So the resultant output is named as PCM or pulse code modulated signal. However, it is worth mentioning that many authors, they prefer to use PCM and quantization terms interchangeably. So sometimes PCM is also used to indicate the quantization process as well. So how we generate the pulses from the sample data? So as we have mentioned that we generate the binary digits at the output, and next stage is to represent the binary digit by some waveform, because in the baseband transmission we need to transform the pulses the binary digits in form of pulses, so that those pulses or those waveforms can be transmitted over the channel. These pulses, they are named as line codes in telephony. So what are the line codes or what are the signaling formats? They can be used to represent those signals. So here is a brief summary for such codes. Actually, there are a number of different types of waveforms that can be used in this particular scenario. However, it should be understood that we need to use two different pulses in order to represent two different binary digits, that is 1 and 0. So basically what we need to have two different types of pulses, one to represent binary 1 and another to represent binary 0. These pulses are broadly categorized in two formats. One is called NRZ, which is the short form of non-return to zero, and another as RZ, which is a short form of return to zero. For non-return to zero, the pulse width exists for entire symbol duration or bit duration. So you can see that this pulse exists for the entire duration. However, for return to zero case, the pulses, they exist for only half of the bit duration. So pulse is at the initial half, and the rest of the half part is 0. So these are some commonly used formats, signaling formats that we use. So first is unipolar NRZ. Unipolar means we use a positive amplitude to represent binary 1 and a 0 amplitude to represent binary 0. You can see that the 0 amplitude is representing binary 0. Similarly, the high amplitude is representing the binary 1. The binary 1 is again represented by a high amplitude, and the 0 is represented by a 0 amplitude, and so on. Same thing is observable from RZ. The only difference is that we are using the pulses which are only half bit duration wide. So 1 is represented by high amplitude, whereas the 0 is represented by 0 amplitude here. The next one is also represented by a high amplitude with a half bit period wide pulse. Next one is also represented by high amplitude, and zeros all are represented by 0 amplitude here. For bipolar case, we actually use positive and negative amplitudes. So you can see that the 1 is represented by a positive amplitude, whereas 0 is represented by a negative amplitude. Again, the next one is represented by a positive amplitude, and 1 is again represented by positive. All the zeros are represented by negative amplitude. Similarly, for bipolar RZ, we again use the positive and negative amplitudes, but the only difference is the bit duration is half. You can see that the 1 is represented by this positive amplitude, whereas 0 is represented by negative amplitude. Another one is next one is represented by positive amplitude. Again, the one is represented by positive amplitude. All zeros are represented by negative amplitude here. Another variant of this RZ is named as RZ-AMI. AMI stands for alternate mark inversion. Alternate mark inversion means we use zeros to represent zero. You can see that all zeros are represented by zeros. So we have zero amplitude corresponding to each zero. However, ones are represented by alternate pulses. So first pulse is having a positive amplitude, whereas the second pulse is having a negative amplitude. The next one is having positive amplitude, and next one is having a negative amplitude. So that's why we call it alternate mark inversion. So these are the commonly used signaling format. So just to sum up the discussion, I have provided the brief discussion as I explained in the previous slide. This is a brief description related to the commonly used signaling format, so that you can read it whenever it's needed. So let us take a very simple example. Consider a binary sequence 0 1 0 0 1 0. We want to draw the signaling format corresponding to these formats: unipolar NRZ signaling format, bipolar RZ signaling format, and AMI alternate mark inversion format. So if we try plotting those formats, you can see that for unipolar NRZ we need to use the pulses which are full bit duration wide, and for unipolar we will be using positive amplitude for 1 and 0 for 0 amplitude for 0. So you can see that the zeros are represented by 0 amplitudes. So all zeros are represented by 0 amplitude, and ones are represented by a positive amplitude with a full width of the pulse, which is equal to the bit duration. Similarly, for bipolar RZ, you can see that for bipolar RZ we will be using the half duration of the bit, but for bipolar we will be using positive and negative amplitudes for ones and zeros. So you can see that the ones are represented by positive amplitude, and next one is also represented by positive amplitude. All ones, they are represented by amplitude, whereas these zeros, they are represented by negative amplitudes. Next zero is also represented by negative amplitude. And for RZ-AMI, we know that zeros will be represented by 0 amplitude. So all zeros, they are having 0 amplitudes. So you can see that we have 0 amplitude corresponding to all 0. And for ones, we will be having alternate pulses. So first one is represented by a positive pulse, second one is represented by a negative pulse, next one is represented by a positive pulse. And so these are the commonly used signaling formats in this pulse code modulation. So far, what we have discussed was the binary representation. You can see that all the signals that we talked about so far was the binary, because we were talking about binary zeros and ones. So primarily, what we were needing was two different types of pulses, one for binary 1, one for binary 0. However, in some cases, what we do, we combine some pulses to make symbols. So, for example, if we combine two bits, for example, 0 0 is combined to make one symbol, so it becomes a symbol number 1. 0 1 is represented by another waveform, another symbol. 2 1 0 is represented by waveform number 3, and 1 1 would be represented by issue. So these symbols, so what we have done, we have combined the symbols in form of waveforms. So for this example, we have combined two bits to make one symbol. So one waveform would be used to represent that symbol. So we will be needing four different waveforms. So this type of coding is called M-ary coding, where M is represented by number of symbols that we use. For example, for this particular case, we are talking about four symbols. So that means this will be four array coding. The number of bits that we use and the number of symbols that we use is related with this expression m is equal to 2 raised to power k. So you can see that here we are using 2 bits, combining 2 bits, so k is equal to 2 and m is equal to 4 for this particular case. The symbol rate is kind of reduced in this case, because when we transmit 2 bits, actually we transmit only one symbol. So symbol rate is actually defined as bit rate divided by k. So the good thing related to this M-ary coding is that it requires a relatively low transmission rate, and it low is actually bit rate divided by k. Secondly, the bandwidth requirement is also reduced. For M-ary coding, we need to have a relatively lower bandwidth in comparison to the binary time. However, it has a disadvantage as well, because it has a relatively low signal to noise ratio, and secondly, it can have a relatively higher probability of bit error during transmission. So one application of this M-ary signaling is the representation of pulses in form of different amplitude. So you can see that we have used 8 different pulses starting from 0 to 7. So this is an 8 level signaling or 8 array signaling, because you can see that we are using 8 different pulses, and each pulse is determined by its different amplitudes. Pulses do not have same, rather they are defined by different amplitudes. So this 2, this is 5 and 7. So we have different amplitudes to represent different information. 8 array pulses means we will be combining 3 bits to generate one pulse. So you can see that the equivalent 2 level signaling would be represented like this. These 3 bits, they represent 5. So instead of transmitting these 3 pulses, binary pulses, we would be transmitting only one pulse with a relatively higher amplitude. Similarly, for 7, that would be represented this. Next 5 would be represented by a pulse, and you can see that the 3 pulses, they are now replaced by only one pulse with a different. So this type of modulation is actually called M-ary coding, M-ary modulation, because we are using more than 2 levels for modulation. So the as I mentioned, the advantage is that M-ary signaling requires relatively lesser bandwidth. Instead of transmitting one pulse for each binary PCM, we transmit multi-level pulse, group of pulse k bits. Bit rate in that case is actually RB by 2, which shows the minimum bandwidth, which is 2. Symbol rate is given by this expression RB by K, which is B by 2K. The need of bandwidth is actually, you can see that for this particular case is actually represented by reduced by K factor. So the overall the bandwidth of K. However, we have a trade-off that overall bit error rate is increased. So let us take a very simple problem here. We want to transmit 800 characters per second, where each character is represented by a 7-bit ASCII code. So we want to transmit 800 characters. Each character is represented by a 7-bit ASCII code. followed by an eighth bit for error detection per character. So actually whenever we transmit one character, that means we need to transmit a 7-bit ASCII code plus one additional bit for error detection purposes. So that means one character would be represented by 8 bits. So whatever number of bits would be needed per character would be 8, and we want to transmit 800 characters per second. So we can easily see that the bit rate that is required, that will be this 800 characters per second multiplied by, we will be having 8 bits per character. So overall bit rate which is required in this case is 64,000 bits per second. Secondly, the 8 bit is chosen so that the number of ones in 8 bits is even number. So this is the rule of bit for the time concerned for that. A multi-level PAM is used for m is equal to 16 level. So we are using m is equal to 16 level. M is equal to 16 means 16 is 2 raised to power 4. So that means we are combining 4 bits to make one symbol. For this particular case, we in 4 bits to one symbol. So what will be the symbol rate in this case? You can see that whatever bit rate we have, we can divide it by number of bits per second, or k, which is 4 bits per symbol, in order to calculate the symbol rate for this particular case. So the symbol rate has already been calculated, sorry, bit rate has already been calculated in the previous part, 4000 bits per second. So if we divide it by the number of bits per symbol, which is 4, so we get 1600 symbols per second. It will be so this was a basic introduction how an analog signal is transformed to a digital signal by PCM, which includes several steps. First step is the sampling, and then pass it to quantization, so that we transform the sampled values to a predefined quantity level, and then we use encoder to transform the sampled levels or quantized levels to a specific stream, and then pulse code modulation is used to transform this bit streams in form of pulses or waveform so that it can transmit signal. So we stop our discussion at this stage. Thank you all. Hafiz.